Welcome back, ladies and gentlemen. So we just finished talking about the nature of graphing and why it's useful. Now we're going to take a little bit of time to talk about slope and remind you guys how that works. And then afterwards we're going to talk a little bit about distance time graphs. Okay, so this should be pretty straightforward. Let's clear off some space and let's get to it. You guys are going to be looking at page 33 of your booklets. And hopefully slope is familiar. You guys have been working on it for some time now, 3 years or so, which is, pretty good. Some of you might even remember it, maybe. So, slope, what does it say? Well, the slope of a line or steepness indicates the rate of change of a variable on the y compared to a variable on the x. Okay, this is a fancy way to basically say that the slope is the word we give to how the graph is changing, right? We just erased right here the graph that we had. And I talked about how in some places it was going up, some places it was going down. And the question is, how much is it going up? How much is it going down? What's the rate of change? How is it changing? Is it getting faster, slower, the same? So the slope will tell us how fast an object is going for a position time graph. So it tells us there, that's a key thing, we want to put that in, that the slope will tell us how fast something is going we got to add this part. On a dt graph. Now d, of course, can mean distance. If I put a little arrow in front there, that means now it's position. But either way, the slope is telling us the speed, the velocity, how fast you're going. So what it says next is that a steep line is a fast object. Or faster, I guess, if we want to be a little more accurate. So you'll see there that you guys have got a graph, right, on the right side of the page. And it asks you a very simple question. Which object is moving faster, A or B? Okay, so take a moment, think about it, see what you can come up with, pause the video, ponder. Okay, you probably know the answer, right? It's A. A is the answer. It's very obviously A. Why is it A? Because if we look at the graph, right, it looks something kind of like this. I'll just do two real quick lines here. So here's A, boom. And here's B. Okay, so A is going to be faster because in the same amount of time, covering it up here, in the same amount of time, I will cover a greater distance, right? This here, maybe this one is 10. Well, in the same amount of time, this guy here only went 2. 10 is obviously bigger than 2. So if I cover more ground in the same amount of time, I'm going faster. Make sense? Hopefully. Now, a reminder. The Greek symbol triangle is called delta, right? And it means change in. Now, the slope, you may remember, has been called rise over run. We can also represent this as an equation, right? Rise is the y-axis. That's the y dimension to talk about that last video. It's the up or down. Run is a fancy way to say left or right. You run left or right. You don't generally run up or down unless you are that space alien and or can fly. So what does this have to do with anything? Well, let's take a look at the equation. This is going to be one of those moments for some people where they're going to go, oh! And some people are going to go, yeah, what's the big deal? Skip, ignore. Rise over run. Another way that you guys can write that is y2 minus y1 over x2 minus x1. And that will equal the slope. There's the equation for the slope as we usually use it in, say, math class. Okay? Now, when you guys were in grade 7, you guys struggled with using this equation because you would constantly get the points mixed up, right? And if you remember, when we have a graph, we'll use, here, I'll draw another one. No, we'll use this one. When we're using a graph here, we're looking at points here, right? We would take points off the graph. So let's say we look right there and sure, right there, right? Those are some points on my graph, and we need to get information from those points. So, I'm going to make up a number here. Let's say this is 5, right? This is 5 seconds. That'll be easy. And right here, we'll say this is 1 second. Okay, so we'll make some nice, round, simple numbers. So this point here, okay, we'll do this one in, no, we'll just do it in black. This point here is going to be 5, 10. Hopefully you guys remember that. That's how coordinates work. And this little point here is going to be 1, 2, because we always list it as x and then y. Because that's the order of the alphabet, x, y, z. For those who aren't aware, there is a z when you're drawing a graph. Y goes up and down, x goes left and right. As we discussed in the last video, there's still towards and away, and that's usually z. So it's usually x, y, z. But that's something you don't need to worry about. We're not going to deal with that in this particular course. But, for those who are curious about what's coming up later on in their schooling. So, we've got this point and that point there. What do we do with them? How do we use them? What do they mean? Well, usually when we're breaking these down, we will give these some kind of a number, right? So we could say that this is going to be point number 1. And this one over here is going to be point number 2. Now, we usually say 1 and 2 based on how close they are to the origin or the reference point, right? So this one's closer, so it's 1. This one's farther, so it's 2. Okay. So when we want to fill in our equation here, what do we have to do? We have to be careful because very often people will get this confused. They'll mix up which number goes where. Very often you'll see students do something like this. 1 minus 2 over 5 minus 10. And all they're doing is they're taking these two numbers and they're putting them in up here, and they're taking those two numbers and they're putting them in down here. It doesn't work, unfortunately, but that's often what happens. And that's just what happens when people aren't paying attention. Remember what we've said before when it comes to doing math and physics. Write down the information you know. So, okay, I'll write down my information right here. And I'm going to say that there's x1, x2, y1, and y2. So now I collect that information. x1 is 1. y1 is 2. x2 is 5. y2 is 10. Now that I've collected my information, I can now fill it into my equation. So 10 minus 2 over 5 minus 1. There we go. This becomes 8 over 4, which would be 2. So my slope is 2. There you go. So that's how you would do it, and that's how it works. Now, there might be something here that a couple eagle-eyed people in the audience may have noticed. y2 minus y1. x2 minus x1. Where have we seen 2 minus 1? Where have we seen something like that? Maybe if I change it, maybe if I rewrite it in another way, instead of y2 minus y1, have you seen something like this? t2 minus t1? Or maybe d2 minus d1? Or maybe you don't remember seeing it with 2's and 1's, but maybe you saw df minus di. What does that mean? Some of you maybe have flipped back. Some of you have noticed it. These all mean delta d. So I could rewrite my slope equation up there at the top. I don't have to write it as y2 minus y1. Instead, I could write it as delta y over delta x. And what does delta mean? We just had it written over there. What does delta mean? Change in. It means change in. So what is this saying? The slope equals the change in y over the change in x. That's the actual definition of slope. It literally means that. When you guys were in grade 7, we taught you the equation in black ink at the top there because you guys weren't ready to learn Greek. Sorry. But the blue equation here is what is actually used in your everyday. Because that blue equation is literally the definition of slope. It means the same thing. As I said, some of you are going, oh, some of you are going, Skip, let's finish filling in the notes on our page at least, right? A reminder, as you saw me do here, in order to calculate the slope, choose any 2 points on the graph. So any 2 points on the graph. To reduce the error, choose 2 points that are further apart. Okay? Doesn't have to be super far, but if I choose, as you saw here, I chose 1 point way down here, 1 point up there. If I put both of them in the same place, right, so like one's here, one's there, you're going to get a little bit more error. The bigger the points are, the farther away they are from each other, the better it becomes. The last piece that says the slope of a distance time graph is the speed of the object. So the slope is the speed. And that's the last bit to fill that in. Now, if you guys take a look on the next page, you guys will see on page 34 a whole bunch of practice you guys can do at plotting lines on a line graph. I will try to upload some, answers to that, but the key thing is to remember x then y, okay? So you can put 2 points per little graph that it shows, or just draw it on a separate piece of paper. That's totally fine. Just remind yourself how it works, okay? I'm not going to talk about that, though, much more here. The answers are located for all the slope calculations in the answer booklet. So you guys can check them there. Make sure you're doing them right, okay? So let's move on to talk about distance and time. A distance time graph, okay? So slopes, hopefully we remember how slopes work, right? We've had a lot of chance to practice those over the years. So now we're going to talk about a distance time graph and see how that works. Now remember, the purpose of graphing is to make our life easier. Yeah, as I said, it does require a bit of an upfront investment, but once you get that out of the way, everything falls into place. Now, for the purposes of distance time graphs, we always want to figure out what the patterns are. Any graphs, doesn't matter, distance time, displacement time, position time, velocity time, acceleration time, fish time, whatever graph you're doing, you want to find the pattern. That's always what you want to do. So the first things first is we fill in our information on page 35. The graph shows distance over time. Okay? It is a scalar graph. So you can go ahead and circle that. The units for one of these kind of graphs are going to be in meters for the distance and seconds for the time. The symbol here that I tend to use is going to be one that looks like this. It's not an official symbol, it's just so you know what I'm talking about here, okay? So, the terms, as it says in the box, this is the information we can collect from the graph, okay? So the terms, we'll put here terms, okay? So the distance is one of the things you can get. And you get that from the from the y-axis. AKA whatever number you read off the y-axis, there's your answer, okay? Time is the next one. You get that from the x-axis. Speed you get from the slope. And those are sort of the three things that you're going to acquire, right? Those are the three pieces of information that you can get here. The distance you traveled, the time it took, and how fast you went. That's it. That's all the things you can get. But that's kind of cool in a way because one graph can tell you three things. My thumb's sticking up, there it is. Three things. So that makes it pretty useful, okay? Now, next it says shapes. This is going to be kind of critical because, as I said, the purpose of this is to make our lives easier. So rather than memorize every single graph, don't do that. It's not worth your time. Remember the shapes that you're going to see. And you're always going to see the same shapes. You're going to see a flat line. You're going to see a slope line. And you're going to see a curved line. Okay, they're the three lines. I've drawn them rather than write them. If you want to draw them, go ahead. So a flat line on a distance time graph means not moving. If you see it flat, nothing's happening. A sloped line, on the other hand, means constant speed. And a curved line means constant acceleration. Constant acceleration, of course, in this case, would mean that I'm speeding up or slowing down in some way. Okay? So there you go. Those are the different shapes, and those are the different terms. These are the things you can find. These are the things that a question could ask you to do. It could say, hey, look at this graph, tell me what the time is. Or, hey, look at this graph and tell me what the speed is. And this is the shapes. If you see these shapes, boom, you know what's happening. So, case in point, we've got an example graph on the page there. Okay? So here's our quick example graph, and we're going to have our two colors. One of them just goes like this. And the other one goes like this. And then it's going to ask you a series of questions about them, okay? So let's try taking a look at some of these questions. What information is recorded on the x-axis of the graph? I mean, I didn't put a label on this graph, but what should be the x-axis based on what we just wrote down here? Right? Should be time. So this should be time, okay? So what units is distance measured on that graph? So we look at the graph, and we see that there's a little bracket. In the brackets, it says m. So that means that this bracket is telling you the units. So the units are going to be meters. Okay? What does this graph show? What are the things you can see from this graph? Well, I wrote it right there. There it is. Speed, time, distance. That's it. Those are the three things it tells you. Okay? How does the data shown in the top of the line graph differ from the data shown at the bottom? Put another way, what's the difference between the red line and the blue line? At a quick glance, using the shapes alone, what do we see? Well, the red line is a constant velocity. There's no real change. It just stays the same the entire time. But the blue one has a constant section, then a not moving section, then a constant section again. And the two different constant sections, right, this one and this one, have different slopes because they're different amounts of rise versus their run. This one over here is steeper, the second part, than the first part, which is shallower. It's not as steep. How many seconds does each line on the x-axis represent? So we have to look at our graph here, and we see that the graph looks something like this, right? It's going to go something like, here is 10, and there's one line, and then here is 0. So if this is a 10, and that's a 0, and there's one line in the middle, that means that each line on the graph represents 5. How much further did the faster moving object travel in 20 minutes than the slower one? Ooh, okay, so we got a bit of a math problem here. How much further? Okay, well, first things first, we got to find 20 minutes on the graph. So when we look, we see that 20 minutes is about here. So everything that happens after 20 minutes doesn't matter. I could erase it, and it would still not matter. So there we go. That's all I care about. So when I look up the blue graph and I check on the axis, I see that this blue graph at 20 minutes is at 400 meters. Then I take a look at the other graph, and I see that that graph is located at, what does it say? For 20 meters, it's going to be at 1,600 meters. Now, the question says, how much further? Further. So I ask you to compare them. So I'm not saying that the answer is 400. I'm not saying that the answer is 1,600. I'm saying that the answer is, what is the space between them? What is the distance from here to there? And you know how to do this. You've done this before. You would take 1600 minus 400. And you're going to get a nice solid 1,200. Okay? So there you go, 1,200. That's the final answer to our question. Speaking of question, we've got one left. Why is the bottom line flat between 10 and 20 seconds? Because the object stopped moving. Because it stopped moving, it didn't get as far. All right. There you go. Some pretty quick review. Now, if you guys take a look down at the next page, you guys have got some more examples to try on page 36 and on page 37. And we will sort of leave it there for the moment. You guys can try those. And the answers, of course, are located online in the answer book. And you guys can see how you're doing. And the next time we come back, we're going to be taking a look at position time graphs. And we'll see how they are different from a distance time graph. Obviously, the main difference is one's a vector and one's a scalar, which means, spoiler alert, the main difference is that a position time graph has negative numbers, whereas a distance time graph does not. It only has positive. Okay? So, see what you guys can do. Take a look at the next couple of pages. Hopefully you guys are enjoying some time outside. It's getting much warmer, thankfully. And I'll see you guys next time.